Okay. Hello everyone, my name is Xu Ran, and today I will presenting on a fascinating topic, which is the never-ending contamination, or the radioactivity and half-lives. So let's begin with the definition. So basically, radioactive decay is a process by which unstable atomic nucleus loses energy by emitting radiation. This transformation allows the atom to move toward a more stable state. The atoms that undergo its process are called radioisotopes or radionuclides. This decay happens spontaneously and cannot be controlled or predicted for an individual atom, but it can be statistically predicted for a large group of amounts, which is the basis of half-life, which we will mention later. So there are three main types of radioactive decay: the alpha, beta, and gamma decay. Though each type involves different particles and changes within the nucleus. In alpha decay, the nucleus emits an alpha particle, which consists of two protons and two neutrons, essentially a helium nucleus. This type of decay occurs in heavy elements like uranium or radium. Alpha particles are relatively heavy and carry a positive charge. They can be stopped by a sheet or paper or even skin, but they are still very dangerous. Beta decay involves the emission of a beta particle, which is either an electron or a positron. This happens when a neutron converts into a proton or vice versa. Beta particles are lighter than alpha particles and can penetrate further because they can be stopped by plastic or a few millimeters of metal. And gamma decay is the emission of gamma rays, which are high energy photons. This often happens after alpha or beta decay when the nucleus is still in an excited energy state. Gamma rays have no mass and no charge, but they are the most penetrating and require thick leads or concrete to block. Unlike alpha or beta decay, gamma decay does not change the element. It only lowers the energy of the nucleus. Okay, so one of the key concepts in understanding radioactive decay is the idea of half-life. The half-life of a radioactive substance is the amount of time that it takes for half of the radioactive atoms in a sample to decay. This does not mean that all atoms decay at the same time, because decay is a random process at the level of individual atoms. But over time, a predictable pattern emerges. For example, in the case study, in the half-life of iridium-192 is 74 days. So the times for the iridium-192 to totally decay to stable elements is 148 days. Different radioactive elements have different half-lives. Some are just fractions of a second, while others, like uranium-238, can have half-life of billions of years. So when we talk about the energy release during the radioactive decay, we often use the unit of electron volts, which is EV. An electron volt is a very small unit of energy used in atomic and nuclear physics. It is defined as the amount of energy gained or lost by a single electron when it moves through an electric potential difference, or 1 volt. In more familiar units, 1 electron volt is equal to 1.6 multiplied by 10 to the power of negative 19 joules. That may seem like a tiny amount of energy, and it is, but in the atomic scale, it's very meaningful. For example, the energy of the visible light photons is around 1 to 3 eV, but the energy released in alpha decay can be millions of electron volts or mega electron volts. So let's talk about some of the applications of radioactive decay. Actually, it plays a crucial role in nuclear medicine. In medical imaging, isotopes like technetium-99 are injected into a body. As they decay, they emit gamma rays that can be detected by special cameras to create detailed images of organs and tissues. In cancer treatment, radioactive sources like cobalt-60 or iodine-131 are used to kill cancer cells through targeted radiation. Also, radioactive decay helps us understand the past and track environmental changes. For example, in radiocarbon dating, scientists use the decay of carbon-14 to estimate the age of ancient biological materials, such as fossils, bones, and artifacts up to about 15,000 years old. Radioactive decay also have more applications like the industrial radiography and process monitoring, and they can also be used as smoke detectors. Some smoke detectors use a small amount of americium 241 to detect some smoke particles. However, every coin has two sides. The radioactive decay would also bring some problem to our lives. For example, the health risks, because exposure to ionizing radiation can damage your DNA and potentially leading to cancer and genetic mutations. And also, it will cause some environmental problems and contamination because it can contaminate the environment and have long-time environmental hazards and requires careful storage and management. Also, it has the potential for nuclear weapons because some radioactive materials like plutonium can be used in the production of nuclear weapons and raising concerns about proliferation. Okay, so let's talk about the radiation sickness. For the early symptoms, there are some nausea and vomiting, and some diarrhea and fatigue and weakness, or can even be some fever. It may looks really normal in the early stage, but later stage there will be skin reactions and hair loss and bleeding that cannot stop and confusion, disorientation, and it will. And if the amount is enough, it will finally lead to a death. Okay, so this case study also mentioned a kind of weapon related with radioactive decay, which is a dirty bomb. So, what are the differences between it and a nuclear bomb? Well, a nuclear bomb is a weapon that uses nuclear reactions, either fission or fusion, to release a massive amount of energy in the form of a powerful explosion. It can create a nuclear mushroom cloud and long-term radioactive fallout and kill hundreds of people instantly and cause long-term health and environmental damage. While dirty bombs are conventional explosive like TNT and is combined with radioactive material, which is designed to spread radiation over an area when it explodes. It does not create a nuclear explosion, and the main purpose of it is to contaminate an area with radioactive dust and causing panic and long-term cleanup problems. Okay, so let's talk about the organization of the nuclear energy, which is United States Nuclear Regulatory Commission, or in short NRC. So, established in 1974, it is the federal agency responsible for protecting public health and safety related to the use of nuclear energy and radioactive materials in the United States. The NRC plays a critical role in maintaining public trust in the safe use of nuclear technology, and its work ensures that the benefits of radioactive materials in medicine, industry, and energy are realized without compromising human health or the environment. Okay, so that's my presentation, and thank you very much for listening.